Okay, so hi everybody. I know most of you in here. I've either worked with you before, I've had you as professors, and thank you to my friends that came out, and my mom as well. I have done some research with the Environmental Biology and Climate Change Department, and I have decided to look at the effect of biochar amendment on cedar elm hydration and water potential and soil moisture because of that. So I've included a campus map here. I don't know if we can see it's sort of indistinct, but there's some red squiggles around the campus plots that I was studying here. So there's 5 on-campus plots. I only looked at 4 of them, but we'll get into that a little bit later. That's just where they're spaced out around campus. So I'm just going to share a little bit of an introduction about climate stress here in Central Texas, go into some of the literature I had to look at for this project, and then my research questions that I've been developing for a little bit now, some of the methodology and the research design that went into this project, my graphical results, and then a discussion at the end, since some of my results were a little interesting. So I mentioned this, but I have decided to study specifically cedar elm trees here. They are an anisohydric species, which means that during the day they do not close their stomata, which means they exhibit more water loss. And the benefit to this is that they're able to photosynthesize longer, but it does mean that they get drought stressed easier, which is why they're a good model for studies that include looking at moisture of plants. The trees here don't have the best growing conditions. We have low levels of rainfall here in Texas. We've experienced more droughts recently. We've increased the number of 90-degree Fahrenheit days since the 70s. And all of this is compounding with climate stress to create an overall more stressed environment in the city and in urban areas specifically. So biochar is known to improve soil moisture in agricultural senses, but we wanted to look at here whether it helps any for trees and if it can help hold moisture for trees. So what is specifically biochar? It's a sort of organic, like carbon material that is caused by pyrolysis of plant matter. That's done by heating carbon or carbon sources under very low oxygen conditions, so there's not actual combustion really, it's just sort of getting rid of vapors and gases and organic compounds and that kind of stuff, but it leaves this sort of very porous, like almost charcoaly residue, and this in turn increases the surface area of soil. It allows it to better trap moisture, nutrients, all the things that are enabling trees to grow bigger and healthier. This can hopefully, in turn, reduce plant stress under the drought conditions that we've specified. So these are just a couple of photos of me using the pressure chamber that I did to collect water potential. You can see in the second photo, there's a cut end of a cedar elm stem. So when you're using this instrument, it pushes gas, in this case nitrogen, through the chamber, and it expels water through the pressure of the gas out of the cut end of the stem. So you'll see little bubbles under the lens, and that's how you know at which pressure the plant has its water potential. So mortality of trees has been linked to drought stress through cavitation and failure of their xylems. So if you know anything about veins and air embolisms, that's sort of the same concept, but for trees, cavitation happens when there's so little water that air bubbles form in the xylem, and this can lead to, dead branches that you see hanging off of trees. And biochar can hopefully reduce this drought stress and increase the moisture and decrease risks of cavitation. So my study is contributing towards the current CLIRES project, which is a campus resiliency project, and I will go a bit more into that. So this is a heat map here. I mentioned earlier that we've had an increased number of 90-degree days since 1979. And I mean, Austin is one of the top 10 cities for this, so we're just getting hotter and hotter here in the city, and CLIRES is supposed to help research this and look into the urban effects of this. It's sort of a management thing, and they've studied like humidity levels, and we have a bunch of these on-campus plots where they planted trees back in April 2024. So they've had a couple years of growth. They also amended them with biochar at that time. So they've had a nice couple seasons, hopefully, of growth, and hopefully we can now see the differences between control and biochar. Since it doesn't work immediately, it sort of depends mostly on water availability throughout seasons. Why does any of this matter? If we're losing our trees here in the city, then the city is going to keep getting hotter. There's something called the urban heat island effect. This is caused when cities have a lack of natural green spaces available to them. So parking lots, anything that's covered with impervious surfaces like asphalt or concrete, they are a lot hotter than the surrounding rural areas or like sub-rural areas where there's more trees and grass. And this can cause temperatures in cities to skyrocket 5, 10, 15 degrees hotter than they usually would. And of course, this all puts a lot of stress on the vegetation that we have here in the city. And tree loss, again, hotter, less livable cities, so we need to protect our trees. A couple of gaps in this study. Like I mentioned earlier, there is a lack of literature regarding biochar and larger woody species. This is most of the research has been done agriculturally because it's easier to see the benefits quicker. But hopefully that this kind of soil amendment actually does do something towards these larger woody species, especially in an urban environment. And one of the gaps in this study is that the Eastwoods, or Site 5, was included here, particularly because of ease of access to it, but also because it's less of an urban environment than the other 4 sites around campus. So some of them, such as the Woodward and Congress site, is located directly on that street there near St. Edward's entrance. So that's more of an urban area that I wanted to focus on versus the more forested. Some of the trees are under canopy shade from larger trees that have been there for years. My research questions were, does adding biochar increase the soil moisture near cedar elm trees? And then subsequently, does this increase in soil moisture actually lead to any difference in water potential? So just water potential real quick. You might have seen some of these diagrams before. If you haven't, that's okay. Water potential is higher in the soil, and then it decreases as you go up into the atmosphere. And since these are negative numbers, you'll see that the soil moisture is closer to 1 or like a positive number to 0. And it increases negatively, so the atmosphere is at negative 100. These are estimates for trees. So just keep that in mind, that water potential decreases as you move up the plant and is very high in the atmosphere and is very low in the soil. Too negative of a water potential can lead to this cavitation like I was talking about, and basically the more negative your water potential is, the more drought stressed your plants are. So keep that in mind for the results that I'm going to share later down the line. My methodology was fairly simple. At each of these 4 sites that I studied, there is 1 cedar elm tree that has been amended with biochar. There is 1 that has been kept as a control. I took 3 cuttings from each tree each week, so it was triplicate samples, and then that was for the water potential. For soil moisture, I used a soil probe, and I took 3 measurements at equidistance around the base of the tree, again for triplicate measurements. And the specifics are on the slide. And then there's a little bit more pictures about the study sites. So site 1 is located up on the hill near the big Congress entrance sign. And then this site 2 is next to the baseball field. Site 3 is, again, on Woodward. And then site 4 is behind the softball field. Just some of my analysis, I used R, and I used repeated measures ANOVAs for the water potential since I was repeatedly taking those measurements from the same tree. And then just a simple two-way ANOVA for soil moisture, and then I just did the same replication, same methodology for my spring data. So for the fall soil moisture, it was generally higher in the plots that were amended with biochar. We can see that at site 1, the treatment was significant. At site 4, the treatment was also significant. Unfortunately, at site 3 and site 2, they were not. I suspect perhaps this is not due to the fact that there wasn't an effect, but because there was such a difference between the measurements. For some of them, the soil moisture percentages were reading at 30 for one stick at the site, and then at another probe, they were at 40 or 20. So there was a wide variety, and some of the plots, as you can see, were also significantly wetter. So plots 2 and plots 4 were, their soil moisture range from like 20 to 40, and then at plots 1 and plots 3, they were lower and drier sites between 15 to around 20% soil moisture. In the spring, I don't know what I did, but they managed to be all significant. So I can say definitively now, at least in the spring, that soil moisture is significantly higher in plots that are amended with biochar. I did change the batteries on the probe, as I noticed they were going a little bit at the end of last semester, so maybe that made a difference, but I think perhaps just with the rainfall conditions that we were experiencing here, it probably had some sort of effect. But that's good news. Unfortunately, the water potential measurements, even though, so in blue is biochar and in yellow is the control plots, I forgot to specify that, but none of these results were actually significant, even though the graphs look physically higher, just because of how much disparity there was between each measurement. So the way I did this is, this right here is a picture of the new growth, the new yearly growth that sprouted in the fall. And I tried not to take too much new growth as I was sampling these trees because I didn't want to affect the overall health of the plant. So I was sort of oscillating between new growth and old growth. And the old growth has that thick bark that you saw earlier, and it makes it hard for the gasket to close tightly in the pressure chamber, and sometimes can affect the readouts of the water potential. So in the future, I would do more measurements, or I would take more care to select either only new growth or only old growth from stems. In this one, in site 3, the water potential was significantly different. Now that one is one of our drier sites. That's the one that's along Woodward, so that's next to the retention pond. So perhaps there is a difference there that under lower sites with less soil moisture, there is a higher disparity in the water potential. And I don't know if you can see right here, this is the tree that was amended with biochar, and then this is the control plot. So this one is noticeably bushier, and that's sort of a trend that we can see among all the sites. I wish I had included more pictures. But despite them looking physically healthier, we don't actually see a clear difference in the amount or the water potential between these two sites, which is unfortunate. So what now? Why does this matter? The soil moisture effects, they seem to be more site-specific and season-specific versus having any real effect from the biochar. However, I think it would be worth redoing this study either with the same cedar elm trees and including more measurements or changing the sampling procedures like I mentioned above, because we do see a difference in the soil moisture, and even though water potential is only one aspect of tree health, it's a very large aspect of tree health. If the plant is water stressed, it's not going to grow right. So yeah, that was my study. Thank you all for coming. Thank you, Dr. Concilio, for advising me, and I've known her since I was a freshman. I did research with her over the summer after my freshman year, and that's the reason I added this minor, and now I'm doing my thesis over it, so I'm very grateful for that.
the end you were talking about how some of the biochar trees do look like they're, you said bushy, or like maybe there's more growth. Is it possible that that impacts the water potential in individual branches, like just that there might be more branches?
Yes, it's hard to say, honestly. The trees are receiving the same amount of water, obviously. I think, Roy, they're either irrigation watered or they're manually watered if they don't receive, a quarter of an inch of rain each week? Yeah, so they are identically watered. If they are bigger, they could be using that water a little less efficiently, but I think it does just have to do with the specific growth that I sampled more so than anything else.
I mean, it seems like a lot of your data it's definitely trending in the positive.
Yeah.
So I'm just wondering if there are ways to, reduce that error so that you get significant. So, like, are some of the sites higher elevation at the top of the hill versus at the bottom? I can imagine that would affect the water.
Yeah.
So that kind of
I know it's difficult. Definitely the wetter sites, which are by the softball field and the baseball field, are at lower elevations. They're at more of a risk to flood. I've been out there and they've been noticeably wetter. That's why the soil moisture was so high for some of them. And I tried pooling the data together. It made it less significant, actually, just because there are so many disparities between each site. So, yeah, I think just
Mother Nature is not a control system.
Yeah. That's definitely, I learned that, so.
Congratulations on a great project.
Thank you.
It's really, really fascinating. I get to now invite Dr. Concilio up here, advisor, to say a couple more things about working with you on this project and to give you the cord of stole that'll represent all of your contributions and hard work in the honors program, including this amazing project when you walk at graduation in a few short weeks. So Dr. Concilio.
I want to, before I start with how amazing Liz is, I just want to say also, I think a lot of times we want to find significant results, or very often, especially students, their first projects, they really want to get, and sometimes there's not statistical significance, but I think in this case, there's clearly some biological significance going on, and this study is really important for land management, and in terms of taking the information and applying it and sharing it, I think we could still, like Dr. Graham said, show the patterns are in the direction that we would predict, and particularly since the soil moisture is higher, that's a really good sign. But it's also, if we were to, if we don't see any difference, then that's actually kind of a good thing too, because we're spending money on these amendments, and if it doesn't work, then we don't spend money, and that's good information. So whether or not it worked, it's sort of it's regardless, it's a cool project, and anyway. So okay, so I'm so pleased that Liz asked me to mentor her on this research. Like she said, I've known her since she was a freshman. During the summer after her freshman year, Dr. O'Keefe and I, Dr. O'Keefe, who's now in Michigan, started a project out at a ranch in Spicewood, and a lot of the pressure bomb that Liz used for this project, she learned those skills from Dr. O'Keefe that summer, and we really enjoyed working with her. There was a year or two when I didn't see you, and then she turned up in my honors course, which I taught with Sasha West, which was the art and science and environmental narratives. It was bringing together a poet, Dr. West, and myself, and we would look at readings together with the students and see their writing. It was so cool to see these students creative writing. And Liz is a really great writer in both. And then, because afterwards I worked with her on a research course, and on this research over the last year, like she said, she's got data from the fall. So I got to see her scientific writing and watch her through that process. So it's just, I think this is one of the nice things about being at a small liberal arts school, and particularly for the faculty, when we get to see our students grow through the years, and also to see, with Liz, I think you're the only person that I got to see. No, Grace was also, there's only a few students I got to see in both of those contexts of seeing their creative writing, and it was really special. So I also want to say that Liz showed like an incredible amount of initiative with this project. I really don't feel like I did that much work, which was really, and she would come to me occasionally, like we meet and I'd give her, like, we would talk about kind of the next direction and things, but it was really cool to see her take the skills that she was using, or she was learning in her biochemistry program, so she's a biochemistry major. She has great analytical skills, her statistics skills really strong, all of the graphs that you're making in R, like I didn't write any of that code, Liz wrote all of it, and did all the analysis, and so it was just, it was really impressive. It was cool to see somebody take skills from one discipline and then use it to answer a question in another. And so, because I'm actually in an interdisciplinary program, I'm not EBCC, I'm Environmental Science and Policy, and so this project, the CLIRES project, comes from a project that I work on with Roy Johnson here, the campus arborist, that was informed by like the city of Austin, basically, like this need for our city. We need to find out like how do we manage trees with this situation of drought that we're increasingly seeing, and heat stress, and also like the cold stress in the winter. And so we've looked at a few different things, but with Liz, we were able to look at water potential. It was just like such a cool way to see, to use this project to look at a different type of data that is really informative. And people are going to be really excited to see these results. So I'm so proud of your work. You've gone so far above and beyond what I, like, in terms of just like I said, like you did all this yourself. So you should be very proud. Liz has been accepted to grad school in chemistry at Texas State. She's going to start a master's in chemistry in the fall. And I'm so proud to have worked with her, and I can't wait to see sort of where you go. And so congratulations.